getting rid of, I think.
Okay, we're just going to continue from last time. Take questions later. So this was isomorphisms. All right, so remember an isomorphism between vector spaces is just a one-to-one and on a linear transformation that connects them. Linear transformation isomorphism. I told you guys that every n-dimensional vector space is isomorphic to Fn, right?
Yeah, sure.
Every n-dimensional vector space?
I don't
No,
Why not?
Okay, good. And then, okay, so there's a theorem. This is going to be useful. I'm actually going to do an example in 8.4 using this fact and some other stuff I'm going to mention. So, it turns out that every n-dimensional vector space is isomorphic, right, to Fn. i.e., if U is n-dimensional, then there exists a linear transformation T such that T goes from U to Fn and T is one-to-one and onto. And preserves addition and scalar multiplication. And basically what this means, i.e., U is indistinguishable from Fn. Meaning, everything you know about Fn, you'll automatically know about U once you know that U is n-dimensional. It will actually behave mathematically in exactly the same way. That is the power of the isomorphism. So once you know about Fn, you automatically know about every n-dimensional vector space. If you want to know how specific guys behave, you just define this function t, and you can see how specific guys will relate to other specific guys. But in general, its overall behavior will be the same as Fn. So that's what isomorphic means. It means that there's a map that goes from one to the other. It's a linear transformation, and it's one-to-one and onto. And basically it means that adding two guys in here is the same as adding their corresponding guys over there. Multiplying the guy by a scalar over here is the same as multiplying the corresponding guy by a scalar over there. Mathematically, it's going to be the same thing. So that's nice. And I'm actually going to use this fact and something else. So you'll see this in practice pretty soon. Here's one specific kind of map that can work. If B equals B1 all the way up to N, is a basis for a vector space V, then if I set up this linear transformation, that's just the map that goes to the coordinates. then it turns out T is an isomorphism. So this is one way to connect a random n-dimensional vector space with this guy. Actually send it to the coordinate maps, which we did in 4.6. And again, I'll do an example where we actually go over this again, in case you forget. Here are some examples. Here's your first example. How about the polynomials? So they ask you about polynomials all the time. It actually showed up in a lot of finals. And in an example today, I'll actually use something like this. So basically this means the set of all polynomials of degree n minus 1 or less, that is an n-dimensional vector space, which means it must be isomorphic to Fn. And in fact, I can tell you exactly how it's isomorphic by using the coordinate map. Just look at the basis vectors, 1 times x, 1, x squared, x cubed, so on and so forth. If I look at their coefficients and just turn that into a vector, then this polynomial will behave just like this vector would in Fn. Right? So anything I can do with this polynomial, I can just manipulate this vector in Fn and things will behave the same. Right? So I can go from the space of polynomials to the space of vectors where I know how to set up matrices and do all that good stuff. Right? And I can do all my work over here, and it will be me figuring out things over here at the same time, because they'll behave exactly the same. Another one. Matrices is another one, where you pretty much list the rows in the vector. So something like from n to 2 is an example, to Fn. Notice that M22 is a, what's the dimensions of this? It's a set of 2 by 2 matrices. So give it this way, what's a basis for this? Give me the brain dead basis.
1 0 0 0 0 1 0 0 0 0 0 1 0 and 0 0 0 1.
Right? I can write any 2 by 2 matrix as a linear combination of these guys. How many guys are there? There are 4, which means this is a what dimension? It's a 4-dimensional vector space. This means M22 is isomorphic to F4, the set of 4-dimensional vectors. And there's a natural map here again. For example, if I take T of A, B, C, D, just send this to the vector A, B, C, D. Just list one row at a time. The first row, then list the second row. If you had a 3 by 3, you list the third row, and so on and so forth. And so manipulating matrices over here and doing stuff with them is the same as manipulating vectors of this form and doing stuff with them, the corresponding things. And figuring out what happens here, I can figure out what happens there. Did I have another one? I just had a few more definitions. That's the end of the example. Here's another definition. If T goes from V to itself, right? Domain and codomain are the same. If this is an isomorphism, it is called an automorphism. Another definition. You might see this in your homework. If not, and you're a math major, you'll definitely see these phrases come up again. If T is 1-to-1 and is an isomorphism of vector spaces, it is called a monomorphism. Now, for some of you, you're not going to see much more isms than this. If you're a math major, there are going to be so many isms in the future, it's not even going to be funny. Sorry. I remember being in class sometime and the professor, oh, so this is a diffeomorphism, and then monomorphism, and this is an automorphism. There's so many isms. Yeah, so that's pretty much the end of 8.3. This is the kind of thing that I want you to remember, like some natural ways to map things by using their coordinates. We're actually going to do that in some examples now. Yeah, so the remainder of what we're doing is going to be mostly computational, so that's good. I'm going to talk a little bit about 8.4, just some highlights on that. Where we're going to use some of the 8.3 stuff to actually solve some problems. How about the matrices for general linear transformations? Like so many of the sections in chapter 8, you're just going through 4.6 and putting it in the language of linear transformations, and this is no exception. Some highlights are the following. One equation. That's one important equation to know from this section. I'm going to explain what these pieces are. Where TB represents the standard matrix or a linear transformation. With respect to a basis B, where the basis B is these U guys. So again, this is going over the idea that to figure out how a linear transformation behaves, all you have to do is figure out how it behaves on your basis vectors. And then when you transform those into coordinates according to that basis vector B, you get the standard matrix for T in terms of B. So yeah, just watch what the guy does to the basis vectors and you'll figure everything out. You should recall that if I just write T, this is just the matrix of just looking at what it does to the basis vectors. And you put those guys in columns. Right? Now once you translate these vectors in terms of the basis B, you get the standard matrix in terms of the basis B. There's a second equation. It's more of a notational one. You can find the output of a linear transformation in terms of the basis B by using that guy that I defined before and the input in terms of the basis B. This gives us a way to find the output transformation. Okay, that's all the theory. Know this, know that. We're going to use it as well as the last few things I just defined from 8.3. And we will start with someone familiar. One of the bonus problems from the last test. Let's actually do it. Did anyone actually try any of the bonus problems? You tried the one with the rotation? I know someone tried that. Did you try this one? That L went from P2 to P2? Okay, so here's a linear transformation that goes from the set of all second degree polynomials or lower to itself. So it's an automorphism, and its definition is the following. L of P of T is just 2 times P of T minus 3 times P prime of T. And we're given a basis. Call it B. 1, 3t plus 1, 2t squared. So this is a basis for P2. This is the basis we want to work in. And they just defined a linear transformation. Whatever polynomial you take, this linear transformation will output this polynomial, right? So 2 times the original minus 3 times this derivative is going to be the transformation that we're doing. Okay. The questions were, find the B coordinates of this polynomial. 5 minus 6t plus 4t squared. By the way, I never said this, but this is basically asking you for p with respect to b. That's basically what it's asking you to find. B, it says find LB, the B matrix for L. So I want to find the standard matrix that does this operation, but I want the column vectors to be in terms of these bases, this basis. And part C was compute L of this guy with respect to the basis B, using parts A and B. There are many ways to actually get to this, but it specifically wants you to use parts A and B, which actually means using this equation. Okay. That was the example. I'm actually going to do 2 examples like this from the past finals, and then you can try the rest to see if you really get it. Okay, how about A? How do you find the B coordinates of something?
We call this 5 minus 6t plus 3t squared is equal to k1 multiplied by 1 plus k2 multiplied by 3t plus 1, k3 multiplied by 2t squared, and then you do
Yeah, exactly. Yeah, good. So you take this guy, 6t plus 4t squared, and you want to write it as a linear combination of those guys. So I like writing C's. So it's C1 times the first one, C2 times the second one, plus C3 times the third one. And the coordinates of this guy is just going to be actually C1, C2, C3. All right, so I just want to solve this for C1, C2, C3. Let's kind of group these here. This is C1 plus C2 plus 3C2 times T plus 2C3 times T squared. Now from this you can actually set up a matrix, right? You can get a system here. 5 must be equal to C1 plus C2. Minus 6 must be equal to 3C2. And 4 must be equal to 2C3. Now you could set up a matrix, but this is actually pretty easy to solve as is, right? Because you can just find these guys right away. So right away I see here that C3 is equal to 2. I see here that C2 is equal to minus 2. And I see C1 must equal to 7. This means that 5 minus 16 plus 4t squared with respect to basis B is actually just the vector 7 minus 2, 2. Right? Because it's 7 times 1 plus minus 2 times this plus 2 times that. And I will actually get this. Right? So that's it. That's the B vector. Right? So I know here my P with respect to B is just the vector 7 minus 2, 2. That wasn't so bad. How about part B?
we take A from 1, we put 1 into the equation A, 2 multiplied by 1 minus 3, derivative taken of the 1, and with the rest to do this.
So let's start with the main formula. With respect to B, all I have to do is figure out what does L do to the basis vectors, which is what you were just saying. I'm going to plug each of these guys. So I'm going to want to know, first of all, I will use the fact that AB2 plus CT squared, I will think of that as vectors A, B, C. Right? Just make it easier to write, and it's actually the same thing. It's an isomorphism. So now what I want to do is I want to find L with respect to B. But by the first formula I gave you in 8.4, this is just figuring out what does L do to the first basis vector, which is 1, 0, 0. I'm going to translate that into B. Then what does it do with the second basis vector, which is 1, 3, 0. I'm going to translate that in terms of B. What does it do to the third basis vector, which is 0, 0, 2? Translate that to be in terms of B. So let's start from the beginning. Now let's look at L of 1, 0, 0, right? What does that give you? This is just the L of the polynomial 1. And so what do I have? I have 2 times the original polynomial minus 3 times its derivative, right? Which just gives me 2. That's a constant polynomial. I can translate that to 2, 0, 0. L of 1, 3, 0, just L of 1 plus 3t. So it's going to be 2 times the original minus 3 times the derivative, which is 3, which is going to give me what?
16 minus 1.
Minus 7 plus 6t, right? Which I can translate to minus 7, 6, 0. L of the third basic vector is 0, 0, 2. This is just L of 2t squared. So it's 2 times the original minus 3 times its derivative. So what do I get here? Minus 12t plus 4t squared. So this is 0 minus 12, 4. Now what I want to do is I want to translate each of these to be in terms of the basis B. And once I do that, I put them in columns, and that's my standard matrix. So let's find, it was 2, 0, 0. 2, 0, 0 in terms of P. What do I do there? I just find 2, 0, 0, set it in terms of C1.
Multiplied by 1 plus C2 multiplied by 3t plus 1.
Yeah, I'm going to pretty much do this again. I'll also show you guys how to set up in a big matrix if you prefer that method, but I think these are easy enough to work out here. So this is just constant 2. I want that to be equal to C1 plus C2 plus 3C2t plus 2C3t squared. So this implies that 2 is equal to C1 plus C2. 0 is equal to 2C2. 0 is equal to 3C2. And so that pretty much gives me what? Just C2 is 2, everyone else is 0. So that guy is actually himself, right? So that's the first one. Now let's look at the other one. Minus 7, 6, 0. I want to find that in terms of B. So I'm going to set minus 7 plus 6t is equal to C1 plus C2. I'm just not write this out again. So it's minus 7 is equal to C1 plus C2. 6 is equal to 3C2. 0 is equal to 2C3. So here I get C3 is 0. C2 is 2. C1 is minus 9. So that gives me minus 9 to 0. Is that basis vector in terms of B? I'm going to do the same thing for the last guy. I want to find that in terms of the basis B. So 0 is equal to C1 plus C2. Minus 12 is equal to 3C2. And 4 is equal to 2C3. So C3 is equal to 2. C2 is equal to minus 4. C1 would just be equal to 4. So it's 4 minus 4, 2. So finally, we end up with L of B is just those guys thrown in a matrix. Two, zero, zero, minus 9, 2, 0, 4 minus 4, finally, if I want to find L of 5, 5 minus 16 plus 14 squared in terms of B, I know that that's just going to be equal to L of B times this guy with respect to B, which is going to be 2 minus 9, 4, 0, 2 minus 4, 0, 0, 2 times 7 minus 2, 2 equals, actually write that out earlier, 40 minus 12, 4. Can I get rid of this? Which is equal to 40 times 1 minus 12 times 3t plus 1 plus 4 times 2t squared. Now what you can do, you can check it for yourself. You can verify this. What you can do is you can find L of this guy, right? Meaning you take 2 times this minus 3 times this derivative, and then show that you actually get this guy when you multiply it out. Note. If P equals 5 minus 6t plus 4t squared. This is the end of the problem. That's the answer. Then if you take 2p minus 3p prime, the answer will be, actually wrote out the answer in terms of standard coordinates, I believe, hopefully today. I remember doing it. I think it was 28 minus 36t plus 8t squared, which, by the way, is equal to that. So that was the solution to that problem. To find the standard matrix of a linear transformation with respect to a basis, just look at how it deals with the basis vectors. Then find the coordinates of those basis vectors with respect to the basis you want to work with. And then if you multiply any vector with respect to that b, it gives you the output in terms of b, which is pretty nice. So we never actually have to work in the standard basis and then translate it. We actually get everything by working in B in the first place. Just want to mention some remarks before we move on. Like the way I did this was the way the question asked for it. It was because they said to use part A and B to find part C, but there were other ways to do it. One way is we could have done this. We could have changed from the standard basis our standard basis is S, which would just be this guy, to B. And remember how we did that? We just set up this matrix. I throw the basis vectors for B, 1, 0, 0, 1, 3, 0, 0, 0, 2, and start throw the basis for the standard guy over here. I can find the reducer echelon form. On this side, I will end up with the three-dimensional identity, and on this side, I will actually end up with 1 minus a third 0, 0, 1 third 0, 0, 0 half. And this guy here is my transition matrix. This is a matrix that goes from the standard basis to the basis B. And so what I could have done was I could just take that guy and multiply by this vector. Then if I take that guy, I'm just writing, P of S goes to B of 5 minus 6, 4. The result actually would have been what we got before, 7 minus 2, 2. And for part C, I could have done the following. I could have found L of 5 minus 6, 4. The output of that would have been 28 minus 36, 8. Then to translate this to B, I would just take the transition matrix from the standard basis and multiply by that. And we would have ended up with the answer, 40 minus 12, 4. For part B, I can just set up a system to translate each of those basis vectors with this guy, so going from a new basis to an old basis kind of thing. So I've got 1, 0, 0, 1, 3, 0, 0, 0, 2. And we knew how L dealt with the basis vectors before. It was 2, 0, 0, minus 7, 6, 0, and 0, minus 12, 4. If I found the reducer echelon form of this guy, I would have three-dimensional identity over here, and over here, it turns out I would actually get L of B. 2, 0, 0, minus 9, 2, 0, 4 minus 4. This guy here would have been my L of B. So more than one way to skin a cat. I could have just worked in the standard basis and then just translate my answers with a transition matrix. But the problem required us to do everything in the basis B. But if you didn't want to, you didn't have to. The instructions didn't say. That's kind of how we would look at it. Any questions from this or the previous? Let's do another example. I forgot what final this is from. L goes from R3 to R3. And here's what I know. I know that L of 1, 0, 0 actually gives me 5, 0, 0. I I know that L of 1, 1, 0 actually gives me 6, 6, 0. L of 1, 1, 1. The output is 7, 7, 7. Part A says find L of 2, 3, 4. B. It says find the matrix L with respect to the basis vectors, these guys. So find LB with respect to B equals 1, 0, 0, 1, 1, 0, 1, 1, 1.
Hey, Jhevon, that's like number 1 from like 2007, right?
It's number 8. It's problem 8 from some. I don't remember what final, but it's problem 8 on one. I have the last page printed. So you see something like that on the final. Wait, since L goes from R3 to R3, we can write, we know it's a linear transformation. L of x is equal to just the matrix times x, where A is what size matrix? 3 by 3. Right? Remember, number of columns would give you the input dimension. Right, this is the dimension of the domain. And then this gives you the output dimension. Dimension of codomain. Right, so we know it goes from a 3-dimensional space to a 3-dimensional space, means I can represent it by a 3 by 3 matrix. So my plan is to actually find what A is, and then I just have to multiply A by this guy. How do you think we can find what A is? Ideas?
2, 3, 4 is linear combination of the basis vectors of B. So 1, 0, 0 times C1 plus 1, 1, 0 times C2 plus 1, 1, 1 times C3.
Why are we translating those into B vectors?
You can write any vector with respect to B.
Because in part A, they never ask for this in terms of B, right? This is like standard course.
Yeah, but you want to find it, you can write that way if you want to solve it.
Doing that and then what?
2, 3, 4 is C1 times 1, 0, 0. You're going to find C1, C2, C3. And since it's linear transformation, the L2, 3, 4 is L C1, 1, 0, 0 plus C2, 1, 1, 0 plus C3. And you just take C1, C2, and C3 out. Since we know the linear transformation of 1, 0, 0, 1, 1, 1, I mean 1, 0, 1, 1, 0, and 1, 1, 1. You can write that way. Do you understand what I mean?
I think so. You want to write this?
2, 3, 4 is, yeah, L C1 times 1, 0, 0. Yeah, that way. And then we're going to take C1, C2, and C3 out. Instead of linear transformation. That's
And so basically you're going to have this is C1 times L of 1, 0, 0 plus C2 times L of 1, 1, 0 plus C3 times L of 1, 1, 1.
Yeah, and we can find C1, C2, C3 from we're gonna have a matrix there. 2, 3, 4 is C1 times that. You know, we can find that. In a separate equation, we can find 2, 3.
How would you get to 2, 3, 4 from this?
We're gonna write somewhere 2, 3, 4 is C1 times 1, 0, 0 plus C2 times 1, 1, 0 plus C3 times 1, 1, 1. There is a matrix equation.
Yo, you're forgetting the L?
We have them already. They gave us 5, 0, 0. You don't need the what L is.
Oh, you're saying on this side you're going to plug that in. Is that what you're saying?
Yeah.
So it has to be something else, like K.
No. Can I write?
You're saying this is C1. This is what you're saying here?
Yeah. That.
Plus C3 times.
Yeah, that's gonna be 2, 3, 4. We can find that what C1, C2, and C3 is.
Okay.
After you find that, we're gonna plug that to the right side of the equation. Those equations are different.
Oh, okay. And then you
We know what L100 is.
And
just
so
gonna
this L100 would be
500 plus C.
C2 times 660 plus C3 times 777.
Yeah,
Okay, so you set up this equation here.
that's 2, 3, 4.
So this would be what? This would be C1 plus C2
Plus C3.
plus C3.
And the second
The
one
bottom would be C2 plus
Plus
C3.
I think C1's -1, C2's -1, C3's
That's
4.
C3. That's 2, 3, 4.
And you set this equal to 2, 3, 4.
Yeah.
And what did you get for the C's?
C1's -1, C2's -1, and C3's 4.
C, you said -1,
Yeah, -1, -1, 4.
-1,
Uh-huh.
and +4.
Mm-hmm.
This would be 777. And so what would the answer be here? So it's -5 -6 plus 28. -5 -6 plus 28. This would be 0 -6 plus 28. This would be just 28. And this would end up being 11, 17, 22, 28. Yeah. Good, that can work. It's not how I thought about it. But that does work. A equals, I just set up a system from the beginning. So I call it A, B, C, D, E, F, G, H, I. Because this system is not hard to solve either. So I noticed that here, at A, B, C, D, E, F, G, H, I, times, this is an alternative. This is, what was the first vector? 1, 0, 0. And the result was 5, 0, 0. What's the second basis vector? 1, 1, 0. And the result is 6, 6, 0. Let's write this. A, B, C, D, E, F, G, H, I. The last one was 1, 1, 1.
Yeah, 777.
And the result was 7, 7, 7. Now, because there are a lot of zeros here, a lot of these guys are going to die. It's going to be easier to find them. So in the first matrix here, this is going to be A, D, G. And that's going to be 5, 0, 0. So I know my A is 5, my D is 0, my G is 0. In this one, I would have A plus B, D plus E, G plus H. That would give me 6, 6, 0. But I know my A, B, and G, so I can find my B easily, right? So my B would have to be 1. My E would have to be, right, because my D is 0, my E must be 6. And because my G is 0, my H would have to also be 0. In this one, I have A plus B plus C, D plus E plus F, and G plus H plus I. That must be 7, 7, 7. But I know my A and B. My A is 5, B is 1, that gives me 6, so that means C is 1. My D is 0, my E is 6, so that means my F is 1. My G and H are 0, and so my I is 7. And so that's my matrix A. I can just multiply that by 2, 3, 4. So that's 5, 0, 0.
1, 6, 0.
1, 6, 0.
And 1, 1, 7.
1, 1, 7 times 2, 3, 4. And the answer is going to be the same. 7, 7, 22, 28. It's nice. Several ways to spin the cap. Okay. Always. Part B asks what was L in terms of P. So here I'm just going to use L in terms of the first basis vector. Translate that to B. L in terms of the second basis vector. Translate that to B. L in terms of the third basis vector. Translate that to B. Those are going to be the columns in my B matrix. So it's pretty much the same as the part B of the last problem. So that guy actually gave us one. So I'm going to have to write 5, 0, 0 in terms of B, and then I'll have to write 6, 6, 0 in terms of B. Then I'll have to write 1, 1, 1 in terms of B. So it turns out that 5, 0, 0 in terms of B is actually just 5, 0, 0. 6, 6, 0 in terms of B. Right? You set up the linear combination, you can solve them. This would end up being 0, 6, 0. And if I found 7, 7, 7, this should be a 7, 7, 7. In terms of B, that would actually give me 0, 0, 7. Which means that L in terms of the basis B, 5, 0, 0, 0, 6, 0, 0, 0, 7. Alternatively, again, could just figure out, do a change of basis from the original basis vectors. Between what they changed to, 5, 0, 0, 6, 6, 0, 7, 7, 7. And if I do the reducer echelon form of that, I would get I3. And I would end up with that matrix. It's like solving all those systems all at once. actually took a lot longer than I thought it would. I wanted to start eigenvectors today. Well, that's actually it, the end of class. So go over those examples very carefully. It's really just an application of 4.6. So it's really testing if you know 4.6. Next time we'll do eigenvalues, eigenvectors, diagonalization, and the other stuff. It's going to be really cool. We'll push all questions for Monday. The last test is on Wednesday.
The 18th, right?
The 18th. Which is going to be a mixture of test 3 and 4. So like the first 2 questions would be from test 2, which is just questions on linear transformations again. And then the remaining 3 will probably be from this chapter 8 and the thing we do on Wednesday. Which is not that bad. It's actually very computational, as you can see. It's not a lot of computation. Most of your proofs will come from chapter 4.
Oh no, I think.
That sinks in.
You taking homework today?